Today my goal is to tell you just a little bit. I'm not going to tell you my results, the theorems I've been proving and so on, because this will be very boring. And as you see, the title is not boring. So I want to keep in this line. I hope you find it not boring. But I want to tell you a little bit about what is this kind of mathematics I work with. Like the nature, how it looks like. So not precisely results or boring things. So that's my idea today. Okay, so, it's, so as the title says, so singularities of spaces. So I want to tell you what is a space. What are we considering as a space? Because this can be, well, very vague. We have many options for this. So I'm going to stick with a very particular, simple kind of space. Everything we do can be done for more general, interesting spaces, but let's keep it simple. So I'm going to talk about solutions of polynomial equations. So this is my space. So you give me a polynomial equation like this one, for instance, x squared minus y to the third power equals t. So a very simple polynomial equation. In two variables, x and y, t is any constant. You can think of everything is like real numbers, x, y, t, real numbers. So very simple, a simple equation. And then the question is, what is the solution set of this equation? Also, we are talking about two variables. So the solution set will be something in R2, the plane, the real plane. And it's going to be a curve. So here I'm giving you the curve. So when t is 0, because of course the solution set depends on the parameter t. So if you choose t equals 0, you have this blue curve here. It's like a V shape, a V letter shape curve, right? And if you take any other t, not 0, so for instance t equals 0.1, the solution set is this other black, or I don't know what is the color, black, yeah. So this other curve, which is not blue. so this one is the solution set. So you see, the solution set, of course, depends on t. And you can see that there is a very important, a very clear difference in the shape, in the nature of the shape of these two curves. And it's the following. If you look at the second one, the black one, it is smooth. You don't have corners. So if you pick any point in this curve, anyone, you pick one, please. And then you look very, very close to this point. You press the zoom button in your mind. Many, many, many times you are looking closer and closer and closer at this point. What you are going to see finally? You are going to see a plane. A line. You are going to see a line, right? That's the thing, the good thing this curve has. It is what we call a smooth curve. On the other hand, if you take the blue curve, well, if you pick any other point which is not the origin, then the same thing is going to happen. But if you pick the origin here, the vertex of this V letter shape, then it doesn't matter how many times you press your zoom button, you are always going to see the V letter. It will never be a line, never. It will be always a V letter, right? So it's different. So this point is special, and this happens because you have like a corner point there. So this point is special, it's extraordinary. It's a singular point. So this is what we call a singularity of this space. So here it's very easy because we have only two variables, but what happens if you have three variables? So for instance, our polynomial equation now is x squared minus y squared plus z squared equals t. Okay, then what is the solution set? Now the solution set, since you have three variables, the solution set is something which lies on the three-dimensional space. So when t is 0, this is the solution set. Right? It's like this union of two cones. But when t is anything but 0, you have this solution set. And you see they are very different in nature. So here you have this corner situation, and here you don't. So here if you pick any point you want, anyone, and you look closer and closer and closer, what we are going to see eventually is a plane. But here, in this first picture, if you pick this point, the origin, the central point, it doesn't matter how many times you press this zoom button in your mind, you're never going to see something different from this. This is the picture you are going to see forever, right? So this is a singularity, and this is a space with no singularities, right? They are very different in nature in the sense, for instance, this one, you can contract all this cone to the vertex, to this point. You can contract this to one point. But this one, you can't. This one, if you contract like this, you are going to get a circle. Oh, you are going to get a circle here. So this contracts to a point, and this contracts to a circle. And a point and a circle, they are very, very different in nature, right? So if you are interested in the qualitative type of the solution of your polynomials, as usually we are when we apply this mathematics in applied sciences, they are very different in nature. So, so far I don't need a very well-developed theory because I can do the picture and we can see. But what if these three variables, x, y, and z, what if they are complex numbers, for instance? Then this is something in 6 real variables. So the solution set is something which lies on the 6-dimensional space. So we cannot visualize this anymore. Then we need some tools to be able to understand the solution sets, the spaces, right? So what we do is somehow developing tools which allows us to, for instance, distinguish between these spaces you can get as solution sets of polynomials. So what is the strategy? I'm not going to read this because it's boring. So what is the strategy? And also, if your polynomial can be seen as a function, right? A polynomial is a function, a polynomial function. Then how can you find the singularities? If you are interested in finding the singularities, in this case, it's very easy. You have the gradient vector, because you have this polynomial function is differentiable. Well, if you don't know anything about this, you just don't mind. But it's differentiable. You can calculate the derivatives. Then you can search at the points where all the derivatives are 0, blah, blah, blah. And we can compute. We can, with simple computations, find the singular points. So this is something we do. But what is not so easy is describing, understanding the shape, the nature of the shape of the solution sets. This is not so simple. But usually, the general picture is something like this. So you have, this is the solution set, it's representing the solution set when t is 0. And the other fibers, we call these fibers, the other fibers, you have 1, 2, 3, and here 1, 2, 3. These other fibers, they are the solution set when t is anything but 0, right? And here you see, it's always like this. The singular one is contractible to one point. But the other fibers, they have holes, like this are representing. But what we mean by holes, because we are talking about this is just a representation. These spaces, they have very big dimension. So they are, I don't know, 9-dimensional spaces lying the, I don't know, 11-dimensional space. So how can you compute this? How can you talk about holes? What is a hole? How can you count them? Then we need to develop some mathematical tools. We have some options. My favorite one is the homology groups associated to this. So we associate in algebra to these spaces. Then we can somehow count holes of spaces of very big dimension. Well, it's a theorem. We have this Milnor number. The rank of this very complicated algebraic object we associate to the space. So we can define this and then we can count. So for instance, if I give you this example, the one we were talking about, but now if x, y, and z are complex numbers, so this is a 5-dimensional space in the 6-dimensional space, then how many holes do I have in this Milnor fiber, in this space? You cannot tell you cannot do a picture because it's impossible. But using this theory, I can tell you that this has just one hole. A very big dimension, but we can count these holes this way. So this is the kind of thing we do. And we can also like try to deform singularities, deform the polynomial. So I'm going to give you a very simple example where you can see how powerful these things we do can be. So for instance, suppose you have this family of polynomials, because s is a parameter, so for each choice of number s, you have a different polynomial, right? This is the solution set of the polynomial when s is 1, and this is the solution set of the polynomial when s is 0. And they are very different in nature, right? Very different curves. And this happens because the Milnor number, that ugly number I just showed to you, they are different. Here the Milnor number is 1, and here the Milnor number is 2. So this is why this is happening. But we have a very good theorem which tells us that if in your deformation your Milnor number is not changing, then the topological type is not changing. It's this very boring theorem here. But it says what I'm telling you. So if the Milnor number is not changing, then the topological behavior, so the nature of the shape is the same, it's not changing. And this is very useful. For instance, if you are working there in your problems, applied problems, and then you come up with this polynomial equation. And you need to understand, for some reason, in order to be able to understand your problem, you need to understand the nature of the shape of the solution set of this very ugly polynomial. It looks very difficult, right? And it is very complicated. It's a very big one, very difficult to understand the shape of this. But I give you also this other polynomial, which is much simpler than the first one, right? So, of course, if you can get to choose studying the solution set of this or the solution set of the second, you are going to pick the second one, right? It's much easier. And the thing is that, thanks to that theorem, they are the same. The topological type, the shape of the solution set of this polynomial is the same as this one. So this is very good. So this is simplifying your life. Yeah, this is just to give you a glance at what we do in this kind of math. I want you to see that it's not numerical, it's more about ideas, concepts, and there is a very strong geometry behind all of these. And I just want to tell you what I work with, so you get to know me a little bit better. Tak.